Hello, I'm Roland Gordon, and thank you for watching the Understanding Optical Time-of-Flight Technology for Distance and Range Sensing training video. In this video, I'll discuss the time-of-flight principle and briefly talk about the different distance and ranging technologies. Following that, I will do a deep dive into optical time-of-flight technology and go over some of the key benefits when using it. I will end the video sharing the typical applications that use optical time-of-flight and share with you how you can better familiarize yourself with the technology. If you're not familiar with time-of-flight technology, simply put, it is using a reference medium such as light or sound and measuring the time taken for the medium to travel between the sensor and the target to determine the distance. Since the speed of which the medium travels is constant, the time delay faithfully represents the distance traveled. When the emitted source bounces off the target, you get a reflection back towards the source. This is the same phenomena as when you yell into a large cave and you hear an echo in return. When sensing distance and range, there are many types of technologies that can be used. The most popular are inductive, capacitive, ultrasound, millimeter wave, and optical time-of-flight. Inductive sensing is based on a coil and an oscillator that creates a magnetic field. When a metal object enters the field, induced eddy currents in the target generate an opposing magnetic field, which causes the amplitude of the oscillation to decrease. Like inductive, capacitive sensing uses the oscillator, but is linked to two conduction plates positioned to operate like an open capacitor. As the targets enter the electric field, the capacitance of the two plates increases, causing the oscillator's amplitude to change, just as in inductive sensing. Ultrasound uses sound as a reference medium that reflects off the object and is returned to the sensor. The length of time that it takes for the sound wave to return to the sensor is an indicator of the distance of the target. Based on the transducer chosen, different field of views and accuracies can be obtained. Millimeter wave uses radio frequency waves in the millimeter range, transmitted from an antenna and reflected off a target back to the receiver. The time it takes for the signal to return to the receiver is an indicator of the distance, just as in ultrasound. Each technology has specific advantages and design considerations. However, in this video, we will cover optical time-of-flight technology, which has been used for over a century. With this technology, a light emitter and a receiver form the sensing elements of the system. The emitter, typically an LED or a laser diode, sends light pulses that bounce off the target, and part of the reflected light is returned to the receiver, a photodiode. The measured time of the round trip taken is an indicator of the distance to the target. Time-of-flight technology is broadly classified into two types: direct time-of-flight and indirect time-of-flight. Direct time-of-flight, as its name specifies, is a measure of the time delay between the light pulse sent and received using a time-to-digital converter. The light pulses are typically very short and high intensity. As described by the equation, you multiply the change in time from the pulse emitted and the reflection pulse received by the speed of light. This gives you the full cycle of the pulse's light. Dividing by 2 gives you the half cycle, which is the point where the pulse is reflected, or simply put, where the target is. Implementations of this are commonly found in LiDAR applications. Indirect time-of-flight, on the other hand, uses periodic low-intensity modulated light pulses. The periodicity of the pulses is determined by the modulation frequency. The phase delay between the transmitted light and the reflected light represents the round-trip distance to the target, which is measured by the signal processing pipeline. Since the signal processing is done in the frequency domain, several cycles of these low-intensity periodic pulses are required to complete a single measurement. The formula to find the distance when using this method is multiplying the speed of light and the phase shift between the emitted and the received signal. This is divided by the product of 4, pi, and the modulated frequency. When using indirect time-of-flight, there's a distance where the phase shift between the emitted and the received signal is greater than or equal to the emitter period. This is referred to as aliasing, as the two different signals become indistinguishable. To find the max range, or maximum distance before aliasing occurs, you can use the formula shown. The speed of light divided by twice the modulated frequency. If the target is further than the max range, steps must be taken in order to de-alias the signals. When using optical time-of-flight, you are afforded several benefits. Since both types of time-of-flight signal chains, direct and indirect, extract the time travel, the measurements are independent of the signal amplitude. This, in turn, makes the distance measurements independent of target color and reflectivity. Also, being that optical time-of-flight uses light waves as a reference medium, the system speed is predicated on the speed of light. This, compared to other distance sensing technologies, is very fast and allows for reliable detection of fast-moving targets. In addition, this technology has the ability to perform very well in high ambient light conditions and is unaffected by humidity, air pressure, and temperature, making it a viable solution for both indoor and outdoor applications. Optical time-of-flight also gives you the benefit of flexibility. You are able to customize the optics of your system for optimal performance. You have the ability to select emitter types, receiver types, and lensing. By choosing your emitter and receiver, you can easily obtain the desired field of view. The emitters and the receivers chosen will affect your range, accuracy, and size. Using a complete integrated module allows for small sizes to be obtained. However, they have set ranges and field of views, restricting your flexibility. You can keep the flexibility while obtaining small sizes if you choose through-hole and surface mount emitters and receivers. With all of that in consideration, optical time-of-flight technology can reach ranges from a few millimeters to several meters. The resolution can also be a few millimeters based on several factors such as the lenses selected. Power, though dependent largely on range and field of view, can be low enough to be operated in battery power applications. There are many applications that work extremely well with optical time-of-flight. Applications under the building automation sector, such as video doorbells and ATM kiosks, are a good fit because of its flexibility with field of view and its ability to work with all target colors and reflectivity. Factory automation applications take advantage of optical time-of-flight's fast data rate, while battery power applications such as drones benefit from the ambient light cancellation and low power. If you want to familiarize yourself with this technology, Texas Instruments offers a device called OPT3101. For more information, visit our product folder at ti.com/OPT3101. Here, you will find many tools and documents to help you test and design your system. We even provide an how to use the OPT3101 evaluation module video to help you get started. If you need technical support, visit ti.com/support, where you will find a variety of ways to connect with us. Thanks for watching.